scientific education to communities across the globe and connecting young scientific researchers to collaborate on new groundbreaking scientific ideas. We have, as with today's event, we have numerous events coming up in the future. This year specifically, we are hoping to run numerous events themed around climate change and the ways in which we can tackle the problems that climate change brings in the run-up to COP26, which is happening in November this year. So anyone who's interested in fighting the climate crisis, please stay tuned for that. But today we are joined by Thea Aarrestad. Thea is a researcher at CERN who specializes in artificial intelligence, machine learning, how machine learning algorithms can be optimized for extreme low latency inference on FPGAs in particle detectors. And today she will be talking on the topic of machine learning at CERN. So without any further ado, you can take it away, Thea.
Thank you very much for the presentation, Ryan. And thank you so much for all the cool presentations you're organizing. It sounds like you have an exciting 2021 in front of you. It's great that you're focusing on climate. Okay, so as Ryan already said, I'll be talking about artificial intelligence at CERN. I'm currently a fellow at CERN. I'm a particle physicist, but lately also a machine learning engineer, where I work on everything from processing data from the Large Hadron Collider to doing data analysis, looking for new physics beyond the standard model. So today I'll be focusing on machine learning at the Large Hadron Collider specifically. So at CERN, we do a lot of different things. We have the antimatter facility, we do atmospheric studies, medical applications, a lot of things people aren't familiar with. But I won't be talking about that today because my expertise is really the LHC. So I assume a lot of you already know the Large Hadron Collider. The LHC is a huge particle accelerator, the biggest accelerator ever made by mankind, where we collide protons at unprecedented energies. The only thing that can beat our collision energies are sort of extreme events in the deep cosmos. So we have protons that we accelerate up to almost the speed of light, and then we bring them into collision at 13 TeV, center of mass energies. We bring them into collide at 4 different points along the ring: ALICE, ATLAS, LHCb, and CMS, where CMS and ATLAS are the biggest experiments along the ring. And I work at CMS. So here you see this nice graphic of CMS, where the protons collide here in the very center, where you see this tiny little tube. And then this whole big 15-meter high, 15,000 ton detector is used to measure what those collisions produce. So as Einstein has taught us, all energy is equivalent with mass times the speed of light squared. That means when these particles collide, all their incoming energy, those 13 TeV, gets turned into the mass of new particles. So the protons or the quarks within the protons that collide completely vanish and new particles are produced. And those particles go out through the detector in a collision that looks like this. So here you can see an event display from CMS where 2 quarks, 2 protons have collided, and this is all the things that are produced in the detector. So the reason we do all these things is to probe the standard model. So we have this idealized theory of the universe and what it looks like and what it consists of. And we believe it consists of 6 quarks, up, down, charm, strange, top, and bottom, where you and I, my computer, everything mostly consists of up and down. We have the leptons, electron, muon, tau, and the neutrinos, where matter as we know it mainly are these things. And then the forces between them. So the photons, we all know, the gluons, it's the interaction between the quarks. Then since 2012, we also have the Higgs boson. So the Large Hadron Collider was essentially built to discover the Higgs. The Higgs was proposed in 1960, and we never had the opportunity to discover it in other ways. So that's essentially the reason LHC happened. So all these particles have a huge range of different masses, making our task extremely hard. So the heaviest particle is the top quark, 172 GeV. And the lightest particles are the neutrinos. And this is an order of 10 to the 9. So it's a huge, huge. Okay, so that's what the particles look like. How can we identify them? So here you can see a slice of the CMS detector. So the particles collide here. I hope you see my pointer. This is where the particles collide, and then they go through the detector, and we use this different detector material to identify which type of particles we're talking about. So we have the silicon tracker, which reconstructs charged particles, electromagnetic calorimeter, which can reconstruct electrons and photons, Hadron Collider, which reconstructs quarks. Then we have a huge magnet, which bends charged particles, and it bends them because we want to measure their charge and their momentum. And we can get that if we have a bent track. Then we have the muon chambers in the final end, the muon traverse everything. This is what it looks like. For instance, if we have a muon produced in a collision, it will go through the whole detector, even through the magnet we have. This is the strongest magnet on Earth. And it will go through the muon chambers and create little signals in each of these detectors. So then we know, okay, we have a muon was produced in the collision. The quarks leave some tracks in the trackers. Some of them, they produce particles that are, some of them charged, and then leave all their energy in the Hadron Collider. And detecting particles this way is how we detected the Higgs boson. So the Higgs can decay into photons. So you have the Higgs decaying. We don't never see it directly, but it decays into two particles that we can see. And then we take the invariant mass of these two, and it should manifest itself as a little bump around the Higgs mass. So the Higgs is 125 GeV. So we have this little bump of events around the Higgs mass over a smoothly falling background. And this is usually how we say we detect a new particle. So if there, for instance, was a new particle that wasn't the Higgs, we would maybe have a bump somewhere else in the spectra. So this is a lot the work that I'm doing on a day-to-day basis, looking for bumps. So the photons that we just saw before when the Higgs decays looks like this in the detector. The photon has no electric charge, so it leaves no signature in the tracker. It is not curved because of the magnetic field, because it has no charge. And it leaves a little signal in the electromagnetic calorimeter. So this is how we say we see a particle. Okay, so I just said we have a complete picture of the standard model. Now with the Higgs boson, every piece is in place. So why am I still at work? Why does the LHC still exist? What are we looking for? So we know the standard model has some issues and it can therefore not be complete. We're thinking that it's maybe an efficient theory and that there's a deeper underlying theory. And some of the reasons for that is, for instance, that we cannot incorporate gravity, at least not in a renormalizable way. So we want gravity to be described in the quantum field theoretical framework, but we can't do it. So we're looking for instance, particles like gravitons, which would mean that it's a quantum field theory and it could be part of the standard model. We also have no clue why gravity is so much weaker than the other forces. And that always strikes people because gravity is the force that you feel the most. You don't really feel any of these other forces. But it really is the weakest force out of the ones we know, and we have no clue why. Then finding the Higgs was great, but it was also troubling. And that's because it had a mass we weren't expecting. The Higgs mass of 125 GeV doesn't really account, it's not really what we calculated in the standard model framework. So we would like the mass to be higher, but it isn't. So in order for it to fit nicely in the theory, we have to put in some fine-tuned number to cancel out the missing mass, let's say, which is a big factor. It's 10 to the 16. So it's a big cancellation. So currently at LHC, we're busy with doing precision measurements, really measuring all the things the standard model predicts very, very precisely. And we also search for physics beyond the standard model. So we call it new physics, new particles, BSM, beyond standard model physics. And that's the biggest concern at the LHC at the moment. So I'm here to talk about AI, AI/machine learning, same side of one coin, two sides of one coin. So where and how can machine learning help with all this? And so just to make sure we're all in the same page, I wanted to do a quick recap of machine learning. So machine learning is a really simple, trivial concept. All we want to do is let a machine learn features from raw data. So we want to learn the machine to map some vector in Rn onto some other vector in Rm in some other dimensional space. So let's say you have some input. It can be a picture of a cat where this picture has some pixelation. Let's say it's 25 by 25, and it has 3 channels, so red, green, blue. And all those things are just numbers. And then we want to say, okay, can you learn a function that takes this input X, like some RGB pixel values, and maps it onto a 2-dimensional vector, which is a probability that this picture is of a cat or the probability that it is of a dog. And everything we do, not everything we do, but usually for deep neural networks, this is true. It's that simple as this. Okay, so the way in which we do this is that, okay, let's say you have some true function that maps the picture of a cat to a probability that the picture is of a cat. You train a deep neural network to approximate that function, the function taking picture of cat to probability of cat, by some weights you learn from training data. So you have the input, this is just the pixel values of the cat picture. You multiply it by some weights. You sum all of them in a neuron. You apply something called an activation function, which we basically just do to get nonlinear outputs. And then it gives you some output value. And that's all a deep neural network is. So you again here see the full matrix multiplication. Here it's just the numbers of that cat picture, weights that the machine will learn the best value of, and then some offset, and then you apply an activation. So it's really, really quite simple. So the way you can learn the weight. So let's say Y is the truth if that picture was of a cat or a dog. And Y hat is the deep neural network's guess of whether the picture is a dog. So the training is to iteratively modify the weights in the network so that your guess is closer to the truth, where closer is the key of the neural network. It's a loss function that you minimize during the training. So let's say up here, you say, oh, the difference between my guess and the true value is really, really big, and I want it to get smaller. And then you kind of work your way down, down to the minima of this loss function. And then that weight configuration, making your probability close to the truth, is what you store and then use for inference. And this way of changing weights is what's called gradient descent, which is kind of the essence of deep learning. Okay, so you saw one neuron, and usually we have a bunch of neurons in a bunch of different, in a bunch of hidden layers. So here you use your input, your picture of the cat, and then you pass it through one hidden layer with a bunch of neurons, and then that passes its output to another layer. And this means you can learn more and more complex functions, and you more and more approximate how our brain works before you finally give an output, say probability cat or dog. So for instance, this can be, take the signals in a particle detector as input, the whole thing, pass it through a neural network, and just give me from all of this input 2 values. Is this a top quark or is this a photon? Incidentally, this is a photon because all the charge is in the Hadron Collider. If it a top, if it was a photon, the charge would be here. So the reason why this is very, very interesting is, of course, they can be highly accurate, but also the latency, the time it takes to compute is usually faster than other ways of reconstructing events. So if I would use all my physics knowledge, like I know a top would be here and have this energy, that would take me an order of 100 milliseconds to a second. Whereas for a deep neural network, this could take microseconds of time. So it's way faster. So we want to use deep neural networks as very fast and very accurate approximations of classical physics, essentially. So deep neural networks have grown to be huge. There's been an exponential growth in the last couple of years to make the models more and more accurate because we have more and more complex things we want to do. We want to have Alexa, we want to do live translation, facial recognition, everything. So currently today, the largest deep neural network has 160 billion parameters, still just 0.16% of a human brain, but extremely large, which means huge computational time and a lot of resources. And usually you do this training maybe once, so you do have infinite time and resources. But there's a lot of places you do not have infinite time and resources. So let's look at autonomous vehicles. There you have a millisecond to decide if you're going to brake for the person walking in the street, if someone's crossing the street, if a car comes in front of you. For your smartphone, just for user experience, you don't want to wait for ages for this live translation. So usually you have a little chip on your phone that is a dedicated AI chip, and it has to do things in milliseconds too, because that's usually as fast as your brain can process things. Then on the extreme edge is high frequency trading. So there are deep neural networks running on dedicated hardware called FPGAs. I'll talk more about them later. And they have to make decisions buy or sell in nanoseconds. If not, they lose millions of dollars. So this is called real-time AI. That's where you have extremely low latencies, meaning you have to do things fast. You have to use little power because you don't want to drain the battery of your phone. And you have not a lot of space to do these things. And we call this edge inference, so computing on the edge. So the realist inference device on the edge I can think about is a particle detector. The Reconstructing LHC particle collision data is an extreme task where you have 200 collisions occurring every 25 nanoseconds. And so this is really a place you want to do good AI. One of the things that will make this even more complicated in the future is that we're upgrading the Large Hadron Collider. We're currently here in a long shutdown. We're upgrading the full LHC to produce more collision in a given time and in a given region of space. And then we will start taking data again, say, end of this year, beginning of next year. After that, we'll have another long shutdown, and then we will do a huge upgrade of the full accelerator complex to something that we even give a new name called the High-luminosity LHC. And then we'll go from what we have today, which is 40 collisions every 25 nanoseconds, to an average of 200 per 25 nanoseconds. And we need to disentangle all of these things from one another to reconstruct which particles we saw in the detector. So it's an extremely challenging task for the future, and all of our effort is currently going into this project, which will be a huge feat. Okay, so we have our edge device, which is this 200 collisions every 25 nanoseconds. Per collision, there's roughly 10 to the 3 particles. We have 10 to the 8 sensors, so millions of sensors. We have a huge data rate, so the whole Netflix library in a second is produced, and we only have microseconds to produce to process this. So that's the difference between autonomous vehicles. If we have 1 day to do an inference thing, they would have thousands of years to do it. That's how extreme our latencies are, which in comparison with smartphones or autonomous driving. Okay, so how it works when we collect this data is the following. So on the detector itself, we have this extreme data rate and very low latency. And every processing we do on the detector has to happen on custom chips that are inside the detector. So the machine learning we do there is on something called ASICs, custom chips that can tolerate high radiation. And all this data, we cannot save it because it's simply too much data to be stored on the resources we have. So we have a processing system called the trigger. So all this data is sent out into the level 1 hardware trigger. And the job of this trigger is to take all the events that we got from the detector and select only 2.5% of the most interesting events and just remove all the rest. And this has to happen ultra fast. And everything we do here is done on something called field programmable gate arrays because they have to be so fast. So that means we only keep 2.5% of the events. And you would think that's enough and the rest we can store, but it is not. It is still too much. So that data is again sent to the high-level trigger. And the high-level trigger is a huge computing farm consisting of CPUs and GPUs, which takes 1% of everything that was selected here and passes it on. And the rest, 99%, is discarded. And here we have hundreds of milliseconds to make a decision as a self-driving car would. Then finally, we have reduced the event rate enough to store this to tape. So in the end, only 0.02% of the collision events are kept for offline analysis. So we reconstruct the full event and do machine learning offline. Okay, so let's go to the detector itself. So on the detector, we have this extreme amount of data. And one thing that's not obvious is that this is also a high radiation environment. It's like outer space and worse, because we have these particles colliding at extreme energies. And we need to cool the whole thing to minus 30 degrees to stay safe from this radiation. So for instance, in the detector, we have a new calorimeter. So if you remember, the calorimeter is this thing that measures the quarks and the electrons and the photons. We will have a new one which is extremely high resolution, which means we can do better with physics. We can reconstruct it better. It has 52 layers and it has 6 million output channels. And it's only limited the amount of data that we can send out of the detector. Now the whole thing needs to be cooled down to minus 30 degrees. That's because those silicon sensors cannot tolerate the high radiation, and they can tolerate it better if they do not heat up. We need to keep everything extremely cold. So if we want to do machine learning here, we need something that consumes very, very little power. So we need these ultra small and very low power deep neural networks that run on custom chips. And they also have to be extremely small, these little chips, because if they get in the way, we cannot really detect the particles. The particles will just scatter on the chips themselves and we can't see them anymore. So one of the things we're doing at LHC is that we take this detector information. So let's say this is just one layer of the detector. It has all these different sensors, and we turn it into a representation for a deep neural network. Then we let a deep neural network encode all the information in this detector layer into a very small space. So let's say you have an input, which is huge. Say you have the cat picture, which is 28 times 28 times 3 in dimensions, and you compress it down to a dimension of 5. So just a fraction of the original. Then you have a really compressed form of the data that was produced. And that you can then send out of the detector without compromising the budget you have to send things out, because we cannot send all the information out of the detector. So we send it out of the detector in a smaller dimensional form, and then we train a deep neural network to blow it back up into its original form without losing the original information. So that's a way of sending data in compressed form using machine learning, compressing it and learning how to decompress it. Okay, so that's an example of what we can do on the detector itself. So really having chips inside this thing that run machine learning. And then those little ASICs, those chips, will send the data out to the level 1 trigger. And here it's really important to remember that everything that's not accepted here is lost forever. So if we have an algorithm that chooses the wrong events, the other events are gone forever. And so here we use something called FPGAs to decide which events to keep and which events to reject. So let's say we have this encoded data. This is now the CMS detector living in this room here. And we have this data that we encoded before. We now send it out to another room next to the detector. So this is now the data in orange here. It's sent out into a room that has the level 1 hardware trigger. So everything is sent via high-speed optical links, because in what we do, the speed of light is a limitation. So you need to make things as fast as possible. And here we have hundreds of processors with big FPGAs to process the data in microseconds. So for instance, here we would do the thing I said before. You'd take the encoded detector data and decode it again. So what is an FPGA? So on the right here, you can see a picture of what it looks like inside an FPGA. An FPGA is just a chip. It has kind of the size of your thumb, looks something like this. And it has a bunch of circuits and resources connected together, and it can do a specific task. They're reprogrammable, which means you can change their functions. You can use them for many, many things, whereas something called an ASICs, a custom chips, you cannot reprogram. Once you burn it, once you put the wires and you make it to do a certain function, you can never change that again. So it contains a bunch of different resources you can use, and you can program it to do basically any task. And before it was only used to prototype something called ASICs, and now we also use it for high performance computing. So why are they useful? So they're useful for the following reasons. You can run them highly parallel, which means it can work on different collisions simultaneously. So let's say you have, this is the one proton beam, this is the other proton beam. They come to collide, and the FPGA can process data from this collision and the next all in parallel. And they're also highly deterministic. So if you would process things on a CPU, sometimes the processing would go faster, sometimes it would go slower. And whereas the FPGAs are repeatable and have a predictable latency. So we can never tolerate that they're slower than 25 nanoseconds, because that's when we'll have a new collision. Okay, so the level 1 trigger looks like this. So it has an input bandwidth of what I said, the total matrix library per second, and it processes information from the full detector. So you have one part that processes information from the calorimeters here in red, one from the muon chambers here in blue, and one from the tracker here in green. And it has 12.5 microseconds to decide whether to reject or keep the event. And as an example, here in the final decisions where we say, okay, we're going to keep the event, we're going to reject it, we have thousands of algorithms in parallel on 10 FPGAs. So it's a huge feat to make all of this fit. So for instance, one of the things we're doing on these FPGAs is, say you have this energy deposits in the detector. This would look something like this in real life. So here you can see 3 particles. You have something called pions and photons, and they're all within 1 centimeter of each other. And we have to be able to say, ooh, which of these energy deposits belong to which particle. So we're using something called graph neural networks, which are able to say, okay, which of these particles left which of this energy. So here, the red energy deposits belong to one of the pions and the blue to one of the other. And this is really an excellent task for machine learning algorithms because it's highly complex. Okay, then we move to the high level trigger. You remember all these CPUs. So here you have more time, you have roughly 100 milliseconds, but you do read the full detector information and you have to run extremely complex algorithms. So here we want to do machine learning on something called accelerators. So the CMS high level trigger looks like this. Here you have the detector. The level 1 trigger sends all its information out when it's selected those 2.5%. And it's kind of scattered. It has some information from one collision, some from another. And in this event builder, we put one full event together. And this full event is then sent into the high level trigger. And this consists of more than 30,000 CPU cores. It's huge. And it runs thousands of complex algorithms, we call them modules, on many, many events in parallel. And it has 300 milliseconds to decide whether we keep the event or we reject it. And here we can, again, only select 1% of the data we get in, and then it's sent out to storage. So we can send out 5 gigabytes per second to storage. That means we have to do a lot of tasks extremely fast, and we cannot do that with the CPUs we have for High-lumi LHC. So we need to be faster. So our current idea is the following. So we have all these CPUs, and then we're going to plug in something called a graphical processing unit to those CPUs. A GPU is good because it can do things highly parallel. So it means things that can be done in parallel can be done faster in parallel on something called a GPU, especially deep neural networks. So what our plan is for high-luminosity LHC is to get the data in to the high-level trigger. Then some of the things we used to do on CPU will move on to the GPU. We have some data coming in from the level 1 trigger. We send it to the GPU. We do some reconstruction on the GPU, which is faster there than on the CPU, and we send it back to the CPU, which means we have more space on the CPU to do things, and things run faster on the GPU. So graphical processing units as accelerators is something we're exploring a lot. So I was mentioning tracking before. So reconstructing particle tracks in the detector is the hardest part we do when we do reconstruction. So here you can, for instance, see we have these hits in the detector. So this is made from one particle, this is made from another, and this is made from another particle. But we don't know which belongs to which. So we need to figure out which belongs to which. And usually deep neural network likes regular inputs like a picture, something that has a regular grid, but these sort of hits are kind of scarce and not regular. So we again use graph neural networks to reconstruct these particle tracks. So we have these hits in the detector, and then we turn them into a graph where each hit has some features, and then we connect them with some connections that the deep neural network can learn. So here on the top, you can see what it would look like ideally if you have 3 different particles, but in reality, we have this extremely high dense environment, and we need to know all of these hits which belong to which particle. So here you can see an example for that. You can see what it would look like trying to reconstruct all the tracks where each of the red lines is a true particle going through the detector. So it's extremely, extremely difficult. Okay, then we come to offline analysis. So here we have infinite time and computing power, and we can run highly accurate and complex algorithms, and we use machine learning for data analysis. So one thing that's extremely interesting with that high luminosity LHC and LHC is that our energy is limited. We only collide the protons with an energy of 13 TeV. We can't give them more energy. But what if new particles are heavier than that? So remember E equals mc squared. So if E is limited to 13 TeV, that means m is limited to something. So if there exists gravitons or new particles, we cannot find them directly because we cannot make them in the detector. E can't turn into m. But there is a way we can look for new physics indirectly, and that's through very precise measurements of things that are very rare in the standard model. So one process that's very rare is called vector boson scattering. And this is so rare that it's even harder to make than making a Higgs boson. And Higgs was very, very difficult for us. What happens is that you have one quark inside the proton that exchanges a vector boson with another quark coming in the other direction. So they exchange this W boson. These W bosons talk to each other, and they make 2 new W bosons. And the quark themselves, they just continue going along their way. And this can happen in quantum field theory in many ways. Those Ws can also exchange another particles, or they just talk to each other briefly and go back out. Or you can think that there's some new particle that talks in between them. And this vector boson scattering is really related to the Higgs mechanism. This is electroweak symmetry breaking. I saw you had a quantum field theory school. So looking at this process is extremely exciting. So if VBS occurs, if this process occurs at a rate that's not predicted in the standard model, it means there might be some new mechanism. There might be some new particle in here that's talking to us. So measuring how many times VBS occurs can shed light on physics beyond the standard model, meaning we can look at particles heavier than this, what we can produce directly. So this is related to the precision measurement part that I talked about in the very beginning. So this is what it would look like in the detector. So you have one quark coming in from this side here. This is the beam pipe. It goes through like this. One quark comes in here. Quark is just the part of the proton that collides. Then you have another quark from the other side. And they meet here in the middle. Then they exchange a W. And then the quark just continues forward. So it's very, very, very close to the beam pipe. It just goes straight through almost. And it exchanges these Ws, and it makes 2 vector bosons come out. So you have these 2 quarks that go almost straight forward in the detector, and then you have 2 vector bosons that go out. So then you have to measure this thing. And when we precisely measure things, like let's say we saw this Higgs bump, as you remember from the beginning, we need to measure how many times the signal event occurs. So these things, vectors go in and go out. And that means we have to get rid of events that look like them, but that are not. And that's also the key job of us as physicists. So this is the signal, and this is just something that looks like the signal, but it's not. And that's extremely hard for humans to make algorithms for, to discriminate two such similar things. It's almost impossible. So what we've been doing in the recent years is to train algorithms that can distinguish between subtle differences, like these 2 Feynman diagrams, which allows us to measure processes we never thought would be possible. Then there's also one thing that's interesting. So I've been saying we search for new physics beyond the standard model, but we're always kind of biased by our assumption of what it looks like. So for instance, with the Higgs, we kind of knew the Higgs would decay into 2 photons. So we looked in the mass spectrum of 2 photons. But what if new physics doesn't look like we expect? What if we just want to know We just want to find anything that doesn't look like what we predict. And that's really, really difficult. So we want to be able to tell anything from the standard model from basically anything that could be new physics. And one could do that using something called anomaly detection. So anomaly detection consists of the following. You let a machine learn what standard model particles look like. So let's say for quarks, you can never really see quarks directly. A quark is always produced and it immediately decays into other particles. So a quark always manifests itself as a spray of particles. We call it jet. We want to learn a machine learning algorithm to know what such a jet looks like. So to do that, we again use this encode decode autoencoder model. So we take the quark jet, we let a deep neural network encode it into a smaller dimensional space. Then we let it learn to decode it. So in the end, it will make the exact same input. So that means you try to compress something into a small bottleneck, and then you blow it back up into its original form. And you want these two to be identical. So what will happen if you get some other spray of particles that's like nothing you've ever seen before, some X? And if this thing goes through your neural network, it will go into the bottleneck. And then when it tries to decode this thing again, that looks completely different than what it's seen before. So it won't be able to do it. It'll make a mess. And that way we will kind of know, okay, that jet is standard model and that jet is a mess. So it must be some new physics we haven't thought about before. Then in order to quantify what's new physics and what's not, you can say, what's the difference between the incoming jet spray of particles and what my neural network produced? And if that difference is large, it means that thing is probably something I've never seen before. And this algorithm can be trained directly on real data, since most of the real data we make is standard models. We can just train the network using real collision events to learn what typical quark jets look like. And that we're currently using a lot in particle physics because we haven't seen signs of new physics yet. So we wanted to look at everything we can think of. Okay, then finally, I wanted to quickly discuss quantum machine learning. So quantum computing, quantum information theory, quantum machine learning is a huge topic at the moment. It's one of sort of the information revolutions. So quantum computing takes advantage of quantum principles. So whereas in classical computing, you have bits or a string of bits. So you have two states, something can be in state 1 or state 0. So it can be, for instance, you can say it's an arrow pointing up or an arrow pointing down. So with classical bits in a computer, if you have 10 bits, you can represent 1,024 numbers. So 2 to the 10. Combinations of 0 and 1. So with that, you can represent just one number between 0 and 1,023 using a classical bit. There's a transistor which can be on or off. With a qubit, you can have many possible states simultaneously due to superpositions. So each single qubit both represents 0 and 1 at the same time. So it can be a little bit of 0 and a little bit of 1. That means that if you have 10 qubits, you can encode all those 1,024 numbers simultaneously, whereas with 10 bits, you could only represent one of them. That means you have a huge increase of information storage possible with using something called a qubit instead of a classical bit. And this has been theorized long ago, and we're still trying to figure out how we can milk this property. Now, one thing to keep in mind is that always when you measure such a quantum state, so you say it's always in both zeros and 1, once you measure it, it will always be 0 or 1. It won't be something in between. So once you measure it, it has a 70% chance of being up, 30% chance of being down, but it will always be 0 or 1. So that means if you want to use qubits, Hi? Ah, okay.
All right, I don't know what happened. You can continue.
Okay, good. I assumed just someone was unmuted. Okay, so that means that you always have to repeat the experiment, and then you get a probability after n measurements. I'll talk more about it on the next slide. Okay, so classically, you have these bits, 0 and 1. You have some logic gate that operates on zeros and ones, and you get an output, which is either 0 or 1. With a quantum logic gate, you operate on this superposition state of all the qubits in the system. every single one. And then the quantum logic gates operates on this full state and gives another superposition state that encodes all the numbers. So we have simultaneous knowledge of the whole system all at once, which is what makes them so powerful. So in order to illustrate this in a more comprehensible way, you can think of it like this. So let's say all these papers here, they're CVs, and you want to find your name on one of these CVs. So with a quantum computer, you can look at all of these CVs at the same time. And each time, the quantum computer will give you a probability of one of these CVs containing your name. So for instance, this one has a 45% possibility of having my name. That means every time I measure the system, in this case, it will be a 45 possibility of being this paper or not. So then I have to repeat the measurements many, many times. And in the end, the probability of the CV containing my name will be so much higher than the other that I will say, okay, this is the CV in the database that contains Thea's name. In classical computing, however, you have to look at each possibility individually. So the computer needs to look at the one CV, then the next, and the next, and the next, and the next, up until it finds a match. So just for databasing, quantum computing has an extreme benefit in terms of time. Of course, you have to weigh the time between repeating the experiment versus doing it once, but taking longer to find it. That's sort of a give and take, but most of the times quantum computing has shown to be superior in terms of speed. So quantum machine learning consists of taking the benefits of quantum computing and use them in quantum machine learning. So whereas in classical machine learning, you have classical data represented by bits, which can be 0 or 1 strings of bits, bit streams. Then you have some mathematical algorithms, let's say a deep neural network, you process them on a GPU and you recognize some pattern. In quantum machine learning, you have quantum data. That means you either have to turn classical data into quantum data, or you just have intrinsic quantum data, which is a superposition of many states. Then you have some mathematical algorithms like a deep neural network. You process it on a quantum computer and you get a bunch of probabilities out. So the question is if quantum computers can speed up the training or the evaluation of machine learning models. And in the end, also, you can use machine learning to maybe estimate properties of quantum systems and use them to develop new quantum algorithms. Because if the machine learning algorithm is quantum intrinsically, you can learn new properties of the quantum computer through the machine learning itself. And most importantly, in science, like Richard Feynman said, nature isn't classical, damn it. So if you want to make a simulation of nature, you'd better make it quantum mechanical. So that means if we want to simulate quantum data, like hydrogen atoms, things like that, having a quantum computer is needed in order to do a good simulation of that system. Okay, so that brings me already to my conclusions. So I hope I've convinced you that we do a lot of cool things with machine learning at CERN, everything from processing the data on FPGAs and GPUs, reconstructing these crazy events in the detector. We explore graph neural networks to do this sort of detector reconstruction a lot. And we're currently now getting more and more into quantum computing and quantum machine learning. And I think it will be really exciting to do AI at CERN in the future. So thank you very much for listening and being here. And I really hope to see some of you at CERN as AI researchers in the future and also just as visitors once this craziness passes over. Thank you very much.
Thanks, Thea. That was really brilliant. Do you have any time to answer questions from the audience?
Absolutely. It would be my pleasure.
Okay, so I think anyone in the audience who wants to ask a question, if you're able to click the raise hand button, which you should see on your screen, and then you can unmute your mic and ask a question, if it's possible.
I was super clear.
Yeah. I think someone raised their hand there, so you can, whoever did that, I didn't see exactly, can unmute their mic and ask a question.
Well, that's okay. I know that. Oh, now I see a hand raised.
Yes, I have a question. Can you explain what exactly what superposition is exactly, meaning how that many numbers are fixed into a single qubit? Like does that happen?
In the end, quantum mechanically, every possibility is possible. So that means if every, let's go back to that. That means if each qubit can always be 0 and 1 at the same time. But it is a probability related to it. So it's, once you measure it, it will always be 0 or it will always be 1. And depending on where it's represented in a vectorial way, so depending on where this arrow of probability points, it can be more likely to be 1 or more likely to be 0. You have a probability, but once you measure it, you will always just get 0 and 1. So it's just a quantum mechanical property where everything that can happen happens. And every qubit is always 0 and 1 at the same time with the given probability, where the probability is defined by where a vector points on this sphere. So it's quantum mechanics. Yeah.
Okay, so we have a question from...
I just want to point out before I end that the main property is that once you measure it, you don't have all the opportunities. Once you measure it, you will always just get 0 or 1. That's why you always have to repeat the measurement of the system, which is why quantum computers are incredibly hard to make, because you have to be able to repeat it. You have to be able to keep the quantum states quantum once you measure them, or they decohere, we call it. You don't have superpositions anymore. So building a quantum computer is extremely difficult.
So we have another question from Mark Laney, who has his mic turned on, so you can ask your question, Mark.
Hi, my question is, are you doing quantum computing at CERN, or are you doing it in the cloud on other provider platforms?
For now, it's just the cloud. We don't have any providers at CERN. Yeah, so it's just in the cloud. But I mean, one of the things we're working on at CERN, which is part of our quantum technology initiative, is really improving the qubits and making components for quantum computers, because that's our expertise, the physics part. But at the moment, it's cloud. Yeah.
So we have a question from Sankarshan. If you can turn on your mic, please.
So my question is that, like, in classical computers, you have a classical determinacy associated with 0 or 1, perhaps, say. But in through quantum machine learning, what are you exactly trying to achieve? Are we exactly trying to make these probabilities more and more closer to 1, or?
Yeah, in the end, you want to repeat. In the end, you just want to repeat the measurement until you get the true answer. And the real power is the amount of information you can store in a qubit. That's the real power of it. So you always store the full information in a qubit, but in order to measure the number classically, you need to repeat the measurement. And that's usually the problem with quantum computing. And one of the bottlenecks we're looking at now is that sometimes it's really expensive to turn this number into something classical, like a real answer. So yeah, it's in a very young state.
Thank you.
Okay, there is somebody else who had their hand up, but I think it's fallen down. Whoever that was, I can't remember. Sorry. You can feel free to ask your question. I think it was Driva.
Yeah. Yes, ma'am. I had a doubt. How exactly are we trying to use QML at CERN? As far as I believe, CERN was like particle colliders and LHC. So
yeah,
are we trying to? Yeah, are we trying to simulate particle collisions using qubits?
Yeah, I mean, for us now, what we do, in order to do what we do, we need a simulation of reality because we have data. So let's say we want to find a new particle. We always have to, in the analysis, say, what do we think the standard model looks like? In order for us to find something not standard model, we need to have an idea what the standard model looks like. So we have simulation of particle collisions of nature. And making those simulations could be finding patterns in quantum mechanical data could be of great help to analyze data that is intrinsically quantum, or to compute, to create data that's intrinsically quantum. So even making simulated collisions, quantum machine learning would be extremely good at, since of course machine learning can also be used to generate data.
Yeah, great.
Yeah.
Thanks.
Thanks.
So I think we have a question from Finn. If you can turn on your mic.
Hi, I'm just wondering, how do you train the initial machine, well, initial AI, to determine what is and what isn't useful or interesting?
Usually that's a big problem for us because we have theoretical predictions. And then we simulate what those, let's say, I think there's a graviton with a mass of 10 TeV. Then I will simulate what such a graviton would look like in all features I can measure in the detector. And then I will simulate what I think the standard model would look like in all those features of things I can measure in the detector. And I'll compare the two different distributions. So it's always just hypothesis testing. So hypothesis 0 is the standard model only. Hypothesis 1 is standard model plus something. So we've always relied on alternate hypotheses. So theoretical ideas of maybe there's extra dimensions, gravitons, dark matter. What would that look like at CMS? So there's always this bias, let's say. Whereas anomaly detection that I mentioned before would help us look for new physics unbiased. So there we would just look for anomalies.
Sorry, can I follow on from that?
Yes, of course.
In which case, do you have to tie up the detector with a single experiment at a time? And
All
if so, how long for?
All the experiments do their own simulations because the detectors are completely different. So everything looks completely different. So we do this completely disentangled from each other. Atlas do their own simulations, we do our own. But so the theoretical part, let's say the mass spectrum of a particle. The theoretical part of that is general. That will be the same for all experiments. How that will look like after going through the detector depends on the detector. So everyone needs their own simulation of the data.
So we have another. Do you have anything else to add, Finn, or like give someone else? I think that's it. Okay, so we have another question from Sankarshan. If you want to turn on your mic.
Maybe it's just up since the beginning, the raised hand.
I think Mark put up his hand again. So Mark, if you have a question, you can turn on your mic.
Thank you, I do. You know, there's a lot of set of algorithms that have been developed for quantum computing, and I'm so glad to hear a lot of questions about quantum computing. I really love it. Can you speak to any new algorithms maybe that are being developed at CERN, or algorithms, you know, in particular for exploring particle collisions?
No, unfortunately not at this stage. It's really difficult to demonstrate quantum speedups, to demonstrate that there is a useful area where this would be extremely much faster than classically. I mean, you can do assumptions. So let's say Moore's law tells us that you have this exponential increase in computing or decrease in the size of transistors. So there's kind of, now we're hitting the limit of what we can do computationally when it comes to anything almost. So I think quantum computing, if we could do it, would benefit us everywhere. But where it can give a direct benefit in simulation of physics data, I can't say. Yeah, for now, we don't have any clear use cases other than educated guesses, unfortunately. But all of these things are a little bit speculations at this point.
Thank you.
Yeah, it's a sad answer, but a true one.
So a question I have is, a lot of sort of media attention has been given to the idea of dark matter or dark energy. So my question is, what relation, if any, does the work of the LHC have to do with this search or study of these new phenomena?
So if there's dark matter, it needs to be a particle if it's part of the standard model, or if we want it to be part of the standard model. If it's a particle, that means we can directly produce it in the Large Hadron Collider, which means we do look for particles with signatures as dark energy. The thing with dark energy is that it's of course dark. which means that it doesn't interact with our detector at all. If it's produced, we don't see it, let's say. So we have to think that dark matter is produced together with something we can see. And there's a bunch of theoretical predictions where you say, okay, I can produce a dark matter particle in association with a standard model particle. Then you detect the standard model particle and you look for some missing energy in some part, something dark. And so there's a lot of direct searches for dark matter happening at the Large Hadron Collider, producing the particle itself.
Mm.
So only dark matter, not dark energy.
I don't see any hands up. We can wait for another short while just to see if there's anyone else.
Yeah, that was efficient the first time. I was surprised. A lot of raised hands after the first minute wait.
So, how is the LHC with the pandemic? Is everything sort of
Everything's closed.
Closed?
Yeah, everything's unfortunately closed. I'm usually a guide there. There hasn't been a single tour for 1.5 years. And so there are no visits. Everyone is home. Switzerland is on a lockdown. So forced teleworking, working from home. So now it's, it's slow, but there are of course a lot of people that need to be there because we are doing this upgrade. So we physically need to wire the detector. So there needs to be people at work that make sure we're on schedule. So some people have to be there to build, technicians.
Yeah. So one thing that I'm wondering, because I know we have a lot of both university and high school students who watch our events. How did you progress from being in high school to working at arguably the most famous scientific institution in the world? And what advice would you give to people who think maybe, oh, I would love to work at CERN as well?
I think just interest. I think just being extremely excited and interested, which I assume people are who are connected to this on their own free will. Having interest, reading as much as you can about what interests you, that will get you where you want to be, I think. Of course, hard work, but mostly just interest and excitement. Take the courses that are right, apply for an internship, a summer student internship, a technical student internship. We're extremely happy to have students. We have many, many programs, both for computer scientists, physicists, even other like human resources, things like that. So look at our webpage. There's a lot of internships there, or just reach out. There's always a way to kind of get in and work on a project, which will give you a good opportunity to stay with us for longer. We're happy to have excited young people with us.
So I think Mark had his hand up for a second there. So Mark, if you have another question, feel free to ask it.
Oh, thanks. On the offline systems, probably is where this is going to happen. Are there technologies like big data technologies that might be familiar to some of us? I mean, ASICs and FPGAs are cool, but I'm trying to think, are you using big data stuff like Hadoop or Elasticsearch or something that's kind of familiar?
Yes and no. Mostly no, because we have our own grid and we have our own sort of computing system. So not so much, but I think it's changing more and more, especially now we're considering using more cloud resources than our own data centers. So we have one data center probably opening right next to CERN, because like I said, in the end for us, speed of light is the limitation. And then you will probably think about using other protocols that are not CERN internal. Yeah, so I think it's coming more and more. It was just before we were the only ones producing this amount of data, before sort of the huge internet revolutions. We built up this huge infrastructure for data storage and analysis and serving. And now we see we can't compete anymore. So I think more and more. It doesn't hurt to be familiar with it.
Thea, yeah.
my mic because I think my colleague wants to speak. Just so
Yeah.
there's no echo.
Hi, Thea. I would like to ask the questions regarding this supersymmetry, and is LHC working for that recently?
Yeah, if
Searching
there's
for supersymmetry and for the Moshless.
yeah, it's still many searches for Susie going on, but the phase space is shrinking. That means that there's fewer and fewer places it could hide away from us. We haven't seen any signs of it yet. And supersymmetry, the principle of it being that you have supersymmetric partners of the standard model partners that are basically the same as the standard model partners. They're further and further away from the standard model particles. So for instance, a supersymmetric particle of the top, the stop, should have the same mass as the top. But for now, we have to assume that the mass is very different from the top because we haven't seen it so far. So supersymmetry is being pushed in a corner. And I can't say that I'm not a huge proponent, unfortunately.
Do you have any other questions, Madhav? Okay. I think if no one else has any questions, or I think Mark actually has something to follow up with, so you can ask your question, Mark.
Oh, one more. I want to know about, is there anything going on at CERN about gravity waves?
Yes, there is. So we have some few collaborations with other experiments. But you could think about gravity waves in the antimatter facility. So look how gravity would interact with antimatter versus matter, how gravitational waves would interact with matter versus antimatter, which is kind of interesting. But that's all I'm familiar with. Yeah.
Thank you.
Okay, so I think we can probably start to wrap things up. So again, thank you, Thea, for the wonderful talk. And thank you for everyone who came along to watch and ask questions. And as always, just keep your eyes peeled to our social media because we always have numerous events coming up in the future. As I said previously, we are hopefully going to run a number of events focusing on the climate crisis in the run-up to the UN's COP26 conference this November in Glasgow. So hopefully, and we'll also, of course, have our usual events focusing on the frontiers of physics and mathematics and computer science. So yeah, just follow our social media and yeah, we'll just finish things off. So thank you very much, Thea, and we hope to see all of you the next event we have. So thanks.
Thank you very much for having me and thanks for listening, everyone. Bye.
Bye.